All the participants are requested to wait. Uh, we will begin shortly. All the participants are requested to wait patiently because we will begin in a couple of minutes. Thank you. অনুব্রত স্যার, hello. Rudrajit sir, অনুব্রত sir, has the speaker joined yet? Has the speaker joined yet?
No, Shimoto Rekha, now not joined. Okay, just wait for some time.
Okay, okay.
Good morning, Shubharnarekha madam. Shubharnarekha madam.
Yes, sir. Sir, yes,
Sir already joined.
sir has joined. Yes, we can begin now.
Tanmay sir is requested to
Please
make him co-host.
Anubrata sir, please make the co-host.
I think we can begin now.
Tanmay sir, are you present, sir?
Hello, hi, I'm present here.
Sir, our honorable speaker already joined. Please make him co-host.
Okay.
Ayun Halda sir already joined.
Okay.
So can we begin now?
Okay, yeah. So
Yeah.
I'm not able to share my screen. Can you please enable me to share my screen?
Uh,
Tanmay
sir,
Babu, please make Ayan Haldar sir co-host. Ayan Haldar sir co-host. Shubharnarekha madam, please start.
yes, yes. A very good afternoon to everyone. Our honorable speaker has joined. So good morning, sir. Today is the last day, the final day of the 5-day FDP organized by Greater Kolkata College of Engineering and Management. So we have come to the very end of the FDP. So we have had many eminent speakers for the last few days. Today we have Oyun Haldar sir. So let me introduce him for a little bit. Dr. Oyun Haldar pursued his BE honors in civil engineering from BITS Pilani with a bachelor thesis from ACRC, Chennai. He was awarded the prestigious Erasmus Mundus Scholarship from the European Commission for pursuing this master among the 10 selected worldwide. Dr. Haldar carried out his PhD on multistable morphing structures using variable stiffness laminates at the Institute of Structural Analysis, Leibniz University, Hanover, Germany. Funded through IRTG program, he was awarded the Samnakam Lode or Excellent Thesis Award for his PhD thesis. He did his postdoctoral fellowship at Cardiff University, UK, Later, he received the Marie Curie Fellowship to carry out his research in Ireland and the UK with funding of about 168,000 euros. Currently, he has been working at IIT, that is PHU, as an assistant professor since 2011. He has over 15 journal publications, 2 book chapters, and over 20 conference presidents and 1 patent. A very good morning to you, sir. You can begin now.
Okay, thank you. Thanks a lot. First of all, of course, thank you for the invitation. It's a wonderful opportunity for me to also share some of my works and share some of the things that have been working. So today's presentation, I hope you can see my screen. Well, can you see my screen?
Yes, sir.
Okay, good. So basically, today's presentation will be somewhat a mix between some of the fundamental things that we normally teach in the course of composites, and also it will be a mix of some of the research aspects where we have been carried out for the last few years. So it will be kind of a mix between both these aspects, right? So if you have any doubts in between, you feel free to interrupt as well, so we can have a discussion. So it's really open platform. The idea is to just have discussions and exchange ideas, right? So welcome again. So the today's title will be on fiber reinforced composites. Particularly, we'll be looking at the manufacturing part, analysis part, and design part. So we'll start with each of these components and look into what are these fiber reinforced composites and how they can be useful in different applications. So there are a couple of books. I mean, if you want to note it down, you can have. I mean, these are the books which I have taken as a reference. But I mean, there are plenty of materials available for this particular subject, right? So, to begin with, what are composites? I mean, it's a very general term, and you might have heard this word in many occasions. So, how we say it is like it's a system composed of two or more physically distinct phases, right? And whose combinations produces an aggregate properties that are different from its constituents. So, this line is particularly important and focuses particularly in these sort of materials that the combinations can be lead to something which is different, right? And then it's heterogeneous at the micro scale but homogeneous at the macroscopic scale. So we'll see in the coming slides what does exactly it mean. So we'll see how the constituents are heterogeneous, but at the same time we can describe in a more homogeneous manner. Then the constant materials have significantly different properties. So what the idea here is, we want to combine different materials that would result in a significant property change. Okay. So the content of these constituents should be generally more than 10%. So we are not looking for a very small percentage of any constituent. So the constituent should be significant. Okay. Now, in this particular course, what we are focusing on is our fiber reinforced composites. So that means composites which consist of a matrix and something like the fiber. Okay. So that is something what we will discuss today. Just a second. So, so as you might see this figure, so this is nothing but it constitutes of a matrix. So matrix is something that surrounds or makes the base of the composite. So it bonds with something called the reinforcement, or which constitutes the fiber. So fibers are the one which are reinforcing, and they are binded over a material that can be of different kinds. This is called the matrix, right? Now, these sort of fibers are generally thin in nature. This is an example of wood. So if you break, so I mean, if you imagine this structure, if you cut a wood and see in the microscopic levels, so what you will find is a structure like this is in the mesoscale. And if you go further deep down in the micro levels, you can really see that there are sort of stranded fibers which are made of cellulose and covered with something called hemicellulose, and then we have lignin fibers, right? So so wood comprises of long cellulose fibers held together by lignin and semicellulose fibers. So all of these comprising materials are weak materials individually, but they become very strong when it's combined together. So if you just take the cellulose fiber, it's not of much use, but if you put it in a binder, of a hemicellulose matrix. So this is your binder or the matrix, the base material, hemicellulose. Then it certainly exhibits this strong material. Okay. So this sort of combination is important in these composites. So again, bone is also considered as a natural composite. So in nature, there are plenty of examples where we have used this sort of composite, different sort of composites, where there is a fiber or reinforcement, and this is embedded in a matrix kind of material, which is the binder. Okay. Now, if you look at today's example around us, especially in the aerospace sector, these composite materials have grown immensely over the last about 10-15 years. So if you look at the new Boeing 787 or the Airbus models of 380, they are all the amount of metal they have been using earlier have been significantly replaced by these sort of composites. And we'll discuss what sort of composites are that they constituents. So if you look at this 787 Dreamliner model of the aircraft, you clearly see that the blue part is the one that represent carbon laminate. So this is carbon fiber and embedded in a matrix. Okay, so it's the same as a same structure as a wood, if you can imagine, or a bone, which consists of fibers as well as matrix. So these are replaced by these kind of materials. Earlier, it normally used to have significant amount of aluminium, or they used to do sort of a material called glare. But now they have been replaced by these sort of composites. And if you look at even in the ship industry, or this is a small example of a kayak, but even in ship industries, larger ships have been now replaced with composites. Now we will see why in the coming slides why this is happening, and what significant properties does it offer in comparison to metallic structure that we are all replacing it by composites. In automobile sector, especially if you look at these sort of racing cars, for instance, the Ferraris or the Maseratis, they have been also been replaced significantly by a carbon fiber body. If you ever play, if any of you are interested in sports, a lot of sports equipments have also been replaced. This is example of a loudspeaker, which is also it's basically made of composites. So now, even in civil engineering, so I come from a department of civil engineering, so we have a lot of applications in civil engineering. For instance, the reinforcements are now been replaced by these sort of composites. Or if you see retrofitting, so the picture in the this particular bottom left side, you see that some people are wrapping over something over the beam. So this is called fiber wrapping technology, where we use this sort of carbon fiber or glass fiber sheets and then wrap it around the existing structure which has already failed or which is about to fail. Okay, something which is already showing cracks or it has deflected significantly. So these kind of composite materials can also help in reducing or somehow retrofitting this sort of civil engineering. Retrofitting by means like repairing, in a sense, these sort of existing. So it's also very important for historic structures or structures that are of very eminent importance, but they are deteriorating over time. Okay. Now the picture on the right is also a picture from a power plant, especially if you have these sort of chimneys. Again, this is a purpose used for repairing of these sort of chimneys, where you offer or you apply these composite mixtures, and they offer you those kind of strength. Okay, so again, few of these examples. Now we will see also that these composites, unlike your steel counterparts, are corrosion free. So if you do a jacketing, or if you do overlap your column with some sort of composite layer, something like this. So this was the initial state of one of the column, and then you wrapped it with this material with fiber reinforced composites, and now it has completely been repaired using this, and they are corrosion free as well. Okay, so now to look a little bit back in the history and see how in general, if you look at how generally materials have evolved over the time, starting from a very long time when humans started their existence to a current contemporary world, we will see that we have been on and off likely using how the trend has been. And if you see that in fact, composites are not something new. It has been used even in the Egyptian. It has been found in the Egyptian civilization or the Mesopotamian civilizations, where several houses, for instance, or several structures have been used made using straws. Straws are nothing but they act like a reinforcement, like a fiber over a binder. Okay. Similarly, these papers they also consist of some sort of a fiber nature, and they are mixed with a matrix. So we have always generally have this idea. But if you look in the between, when after the advent of your industrial revolution, or when we have a lot of metallic structures coming in, these composites sort of reduced or diminished, their usage somehow diminished, and today we are again picking it up, and we are again making different kind of composites where we have fibers of different nature, and also matrix or the binding, the base material also of different nature. And we will look what are these different currently, how we have evolved a lot, and we evolved into different kinds of these fibers and different kind of these materials, right? So there are a few of these examples that I was talking about, like paper has been a part of this papyrus plant. So there is a layer of lignin there. So even if you look at Mongols have been using composite bows that were not made for a single structure, but they have different sort of reinforced bows. Okay, so they are very interesting books. This is a quite interesting book by Vitruvius Polio. It's actually a very classic, a very old book written in that sort of time, but it gives a good idea about how things were being used at those times. So this consists of how architecture was made using different sort of materials, and you can link how materials have evolved over time. Okay. So these are some of the things. Now, especially after the World War time, this fiber reinforced polymer came into a lot of notice. Particularly, people that was the time when glass fiber composites and everything were mostly used. So there are a few of these examples. In 1961, it was the first carbon fiber that was patented and commercially available. So carbon fibers are widely used nowadays, but its advent started around 1960s, and particularly it's been used in aerospace, automobile, and different kind of things, and even in construction industries. Now, just to go a little bit deeper into the subject, so a lot of people think, how is it different from alloy and everything? So, if you look a picture on the left hand side, this is how a microstructure looks in a brass, okay, which is nothing but alloy. So here, if you see that they're somehow, so what we do is we mix these materials that make up this brass or bronze or steel, but their properties entirely change, right? So once you make brass, it doesn't retain any constituent element. It becomes a new element at the end, right? It has completely new properties. Although this significant amount or the proportion does matter what it comes out, but it doesn't really inherit directly any property from there. Whereas, so this is an example of a composite where you see that there are some fibers. Okay. So this is a micro level picture where they have these fibers, and this is embedded in a matrix. Now these are these particularly matrix. I think this is a of a glass fiber reinforced in a epoxy matrix. Epoxy is a polymer. So in a polymer, you have embedded your glass fiber matrix, and if you see that the resultant material that we get, it clearly extracts. So what the property that the glass fiber offers, so the elastic modulus or the stiffness that the glass fiber offers, or the strength the glass fiber offers, is sort of directly inherited in the resulting structures. So the constituent elements, they retain their original properties, and thus it makes it useful for more suitable wider application. Because now let's say you want to make a material that you need a particular range of stiffness or a particular range of strength. So accordingly, you will use your what sort of fibers is required, what sort of matrix is required, that would offer. So you can predict the properties clearly, very distinctly, at the resulting material, the resulting composite, what you will get from the constituent fibers and the matrix. Okay, so this is sort of very important in that sense. Now, going to this reinforcement or these fibers, so particularly what we see is there are different types of fibers that we use. So the most common way of using this is basically the continuous fibers. Okay, continuous fibers is the one, the picture that I showed in the last slide is nothing but the continuous fibers. So here your fibers are long, thin fibers that are going from one end of the structure to the other end. Okay, so it acts like a reinforcement in a way. So these are the different types of fibers. They're most commonly used. But then apart from that, we also use something like short fibers, is also called whiskers. That means these fibers are chopped. Okay, then they are chopped and then they are sort of uniformly distributed. It's not necessary that it will be uniform, but if in a macro level, you will see that it's sort of homogeneously distributed. So you use different manufacturing technique. So let's and you allow these fibers to be uniformly distributed. So although these fibers are now spread all over the surface in a matrix, right, and then you make the composites. So another kind of thing is called particulate. So they are not really these thin nature of fibers, but they are sort of particles. Okay, so in a sort of different sort of particles, these particles also offer distinct properties for the constituent, for the resulting lamina. Okay, and resulting composite that we get. So again, this is embedded in a fiber kind, in a matrix kind of binder, and then this will give a particular property that you're looking for. Now, what are the advantages? Now, this is something very important here. Now, why we are using all these composites, why we are replacing it by metals and things like that. So, what are the clear advantages? So, the main advantage also is that it has got very high strength and stiffness. To be very specific, it has got very specific high strength and very high specific stiffness. Now, what do I mean by specific? By specific, I means that if you divide it by the density, so strength divided by density is very high, or stiffness divided by density is very high. Now, when I say density, that means let's say you have got a same weight of metal and the same weight of sort of a structure made of composites. So the strength it will offer for that particular weight is so within a very less amount of weight, composite can offer equivalent sort of strength or stiffness. So they are very lightweight. That's the thing. Why they are very lightweight? Because they are made of something like a polymer matrix. Right? Polymers are generally very light. Now the strength or the stiffness is primarily offered by these fibers that I'm running. Okay, they are made of different sort of fibers, and they are the one providing the strength and the stiffness of the structure. So as I said, this specific word is very important. That means they are very lightweight, but at the same time, it is offering high stiffness and strength. Okay, so comparable stiffness as metals, for instance. Okay, but relatively light. So again, this is what I discussed. So they are very high fatigue life. They normally and don't undergo fatigue failure. That means if you do a lot of cycles, loading cycles, it doesn't fail very easily, which is again a common feature in metallic structures, right? So they are the thing is thermal insulation or the conductivity is also there, and electrical insulation if you want to have, because it's made of polymer, right? So thermal insulation, electrical insulation, and another important part is the corrosion resistance. If you compare, for instance, if you want to make something which is susceptible to humidity or things like that, or temperature or humidity, I would not take a metallic. It's much advisable to use something like corrosion resistant or these fibers. They are not resistant to corrosion, right? Now, the most important of all of these is the last point, which says that this is the ability to tailor the material properties for optimal strength and stiffness. Now, unlike your metallic structure, which are isotropic in nature, which has got a distinct elastic modulus, which has got a distinct failure, suppose strength, right? All these material properties are sort of fixed, and they are, you cannot really tailor them, you cannot change them, because that is a property of that particular material. But for the case of these composites, you can actually tailor the material properties based on what you want. So not just the values, but also the directional properties. Now, let's say a good example will be this particular figure that I'm talking here. Now, if you see here, let's say you've got the fibers running in this direction. Okay, in this particular direction, your fibers are running. So therefore, naturally, because the fibers have been reinforced in this direction, you will always have a superior property here. So your E in this particular direction, it will be much larger, higher than the E in the other direction, right? Because your fibers are running in the particular direction. So therefore, let's say, but no, you want your E to be higher in the opposite direction, then you run your fibers in the opposite, in the perpendicular direction. So you can really tailor it. So because you're manufacturing it on your own, that means you're laying up the fibers and the matrix on your own. You can really change the direction of the fibers and accordingly change the properties. Okay, so this is something very important. And that's what I mean by the last thing, that you can change your material property. Now, not only on orthogonal directions, you can really have angles. So you can have a 30-degree angle. So let's say you don't want to make this particular figure, all the fibers running in this direction. What you can do is you can make some angle here. You can run your fibers like this. In that case, what you will have some components in X and Y, and accordingly get your elastic moduluses and things like that. So therefore, you have this freedom to tailor. So you accordingly, let's say you want a high shear strength or high shear stiffness, you want to lay it in the 45-degree direction. If you want in one, suppose in this direction you want to have a higher stiffness, you lay your fibers in this direction. So this is about the directional properties. But apart from that, also I was saying that the values also you can change. How you will change the values now? Now, obviously, the matrix the matrix has got a fixed elastic modulus, and your fibers have got a fixed elastic modulus that you cannot change. Suppose you have a carbon fiber, the elastic modulus or the metal property of carbon fiber is going to be the same. And also, if you have got a polymer, let's say thermoset polymer like epoxy resin, okay, or a thermoplastic polymer, it's going to be the same. But if you change the volume fraction, that means how much volume of fibers you're putting inside this whole specimen, then your resultant elastic modulus or the resultant material property will depend on how much fibers you're putting, how much is the volume fraction, right? So that is under your hand. So you can really play around with those things to impart those sort of properties. So if you don't want very high stiffness, don't put much fibers. Okay, so that is very sort of important, and things like that. So if you see again this property that I was saying, specific strength upon specific stiffness. So what do I mean again is like, so if this is the strength divided by density, that is what it means, specific, right? So that is what it means by density, specific, and then this is specific stiffness again by density. So if you see glass, so this is glass fiber, so fibers made of glass. Okay, so there are different kind of these glass fibers. This is S type glass fiber. Now, if you look, it has got a very high specific strength. That means it will not break very easily. So if you compare it to aluminum, which lies low, very low here, so it's around 20, but at the same time your glass has got a specific strength of 200, which is quite high. Now if you look at graphite, which is nothing like it's carbon, so high modulus carbon fiber, if you look at carbon fiber, what you will see that your specific stiffness is around 20. Okay, so it's much higher than what you have in aluminum or titanium. In fact, titanium also is quite low. So if you compare to all the metallics, you are much ahead already. That means it's not like your strength is ahead or your stiffness is ahead. Probably your strength is comparable to these metals, but your specific strength is high. That means it's with very light weight you can achieve that high strength. With a light weight you can achieve a very high stiffness. So that's the whole idea. Okay, so these are different fibers normally what we use, so that we will look. But there are obviously certain disadvantage of this whole composite fiber reinforced composites. Number one is naturally it has got, because to make these fibers it's more expensive to make these fibers, because they have to be very thin and they have to be certain, let's say the cross section, everything. So it makes it more complicated to manufacture them. So it costs more. But as we are increasing more of these productions, things are getting reduced. Now, one of the worst part of these things are they are not environment friendly, because what you're using at the end are polymers are plastics, right? So they are not environmental friendly. The fibers are also, they are glass fibers or carbon fibers and these kind of things. Now, what now we are in the last at least 4 or 5 years, what I'm seeing is there's been a huge amount of research going on how to make this composite sustainable, right? So there's another, probably a lecture for that or another topic to discuss, but there's a huge work going on sustainable composites, where we are using not just polymers, but now with the advent of this biopolymers or sustainable polymers, we are now replacing, let's say, a thermoset, a thermoplastic polymer by a biodegradable polymer or a bio-based polymer, plant-based polymer, right? And also we are trying to replace these kind of carbon fiber or glass fiber by more biofibers, that is something like lignin or cellulose, these kind of fibers, or hemp fibers. These things are more, it's something that a lot of work is going on, and this probably would replace this concern that we have. Okay. Now, although it is sort of insulated by temperature, and then but it does affect, temperature does play a role. Or if you heat it to a very high temperature, because it's ultimately a polymer, right? And then if you heat this polymer to high temperature, or if you put it to subject it to moisture, it will change. It will absorb moisture, and the properties might change, right? So this is again a concern, especially if it's used for aircraft, where there is a lot of difference in the temperature and moisture content. So these kind of things do play a role. Now, the another weak point is the poor strength in the out of plane displacement when matrix carry the primary loads. In the last example that I showed, the strength or the stiffness, they're quite high in the fiber direction. So if you look in the fiber direction, they are quite high, but on the other side, in the other directions, they still become poor. So there is, although you can do some tailoring in that sense, but still one of the directions you probably have to accept that it's not going to be very stiff. Then it leads to this sort of impact damage, delamination. Now, because we will look also now these fibers, what we do is we make different stacking sequence. That means we make one layer and put another layer with a different fiber orientation, another layer with different fiber orientation. Like this, we stack on different sequence. So as a result, you have, let's say, a lot of stacks, a lot of fiber plates, or what we call it plies or laminas. They are stacked upon each other, and therefore, if it's stacked upon each other, then what happens is there is a chance that it separates out. So there is a ply separation or delamination, right? And therefore it's more complicated to repair them than metallic structures. Okay, so and again, this has concerns with low reusability as well. So now let's look into the concept. So I already told you about what are fibers, what are matrix. Okay, so we will again look into the details of these two aspects. But for now, you know what are fibers. There are some fibers. You put them, these fibers, into the matrix in a different directions if what we wish. And finally, you get a structure like this. So this is called UD ply or lamina. Lamina, lamina. That means it's a single layer which consists of fibers in particular directions embedded in a matrix. Now, if you stack in different sequence, so let's say you have, this is your 0 degree. That means it's running in the one direction, it's 0 degree. So first you place a 0 degree, then you place another of the same lamina, which is ply 2, is also 0 degree. Then what you can do is put some 90 degrees like this. So you put 2 0 degrees, 2 90 degrees, and then you place it upon each other. That will create something called a laminate. Laminate consists of many layers. So it's just four, but you can, I mean, for an aircraft structure or for a, if you want to make a beam out of it, you need hundreds of layers, right? They're all stacked in different directions. Now, that leads to the sort of tailorability in the direction. That means in this case, you will have very good properties in this direction as well as this direction, both, because 90 will offer you high strength, stiffness in this direction, whereas 0 will offer you high stiffness and strength in the other direction. But if you need to have high in shear, you probably have to go with 45, let's say. Okay. So based on how you place your fiber orientation will lead to a desired response of the structure. Okay. So this is the main concept where you add fiber matrix, you get a lamina single layer, and from the single layer you get different laminate. You get a laminate that consists of different layers. Okay. Now let's look one by one a little bit in more detail. What are fibers and matrix and what are these properties offers by these? So if you look, I already discussed that in the fiber category, you have particularly three different categories: short fibers, long fibers, and particulates. So there are some of these images that we have taken, let's say, these are like SEM images where in a micro level you can see these fibers and these particulates at a this is about 50 micrometer and this is about 400, and you can even zoom in further and you see how these fibers are, how they look like, how they are. So there's so many fibers which runs in a particular direction, right? And now, if you look in a more macro level, this is how it looks like. You will obviously not see any of this happening, but these fibers do sort of influence, right? And if you see in the laminate level, you see that it breaks. When it breaks, you can clearly see some fibers coming out, and so this kind of behavior is often observed if a sample breaks, where you can really clearly see these are small fibers running out. So within these long fibers, there are different kinds of how we can make these long fibers. So this is called a unidirectional fiber. That means your fibers are simply running in a particular direction. Okay, it's just very thin fibers running parallel to each other. Okay. And then it's kind of these black strips that you see is sort of stitched so that these fibers they remain in the certain place. Otherwise, they will start moving, right? So you have to sort of stitch it in a way. Then this is called woven composite, like uh, like your clothes, right? Woven. Okay, so this is woven in bidirection. That means they are like overlapping upon each other. So it's like it's something like this, where there's one fiber on the top and something goes in the bottom and then comes again on the top. So this is like a woven composite, right? They're also they're quite commonly used because they offer sort of more resistance because of this woven nature or more strength. And this is a woven in three directions, and this is called tri-directional woven. Okay, so this is example of a glass fiber. This one is the black one is a carbon fiber, and these are like glass fibers that have been used. Now, what are the commonly based used fibers? So, let's say you've got few natural fibers, organic fibers, not natural, like let's say they are from organic material, and some of them are inorganic fibers. So, for the organic fibers, we have polyester fibers, aramid fibers, carbon fibers, and then few natural fibers that I was talking about earlier, uh, jute fibers, hemp fibers, cotton, or the cellulose fibers, to say. Whereas on the other hand, we have glass fibers, ceramic, boron, metallic. Okay, so the choice of fiber will ultimately influence the resultant property of the composite that you will get naturally, right? Because each of them are different and they have different stiffness, different strength. Yeah, right. So they will all influence all these sort of things. Okay, thermal expansion, all these things, and also the cost. All of them have different costs. So carbon tends to be very expensive. On the other hand, glass fibers are much more cheaper. Okay, now, so this is a bit of thing that I just wanted to read it out. So that's why I put it like this. So these reinforcements are typically 10 to 100 micrometers in diameters, right? So they are quite thin. It's something like a hair, basically. So e-glass fibers are low cost. So glass are the most low cost fiber reinforcement composites. They are made for amorphous glass. Okay. Now the particular feature of e-glass is a low area density of defects on the fiber subjects. The surface results in the tensile strength up to 3 kPa. So this is something I wanted you to just note it down, because so there's a particular kind. So these glasses are depending on the manufacturability process and kind of glass. So this E glass is something which is naturally has very low defects. So the more the defect, obviously, you will have lower the strength. So it has got more defect, much less defect, let's say per area density of the surface. As a result, this has got one of the highest strength, okay, which is about 3 gigapascal, which is quite enormous for a fiber. Okay, even the same thing holds for your natural fiber like cellulose fibers. They have got very high. We will look into the table, but they are having very high tensile strength, um, about the same range. In fact, more than this. The other type of glass fibers include C glass, which is corrosion resistance, S glass, which is high strength, D glass, which is dielectric, and A glass, which is alkalic resistance. So based on the different kind of glass, different glass fibers offer different kind of properties, and whatever is your application, you might choose one. Now, the carbon fibers, on the other hand, they are widely used in aerospace sectors. Their stiffness can be 10 times that of glass fibers. So your carbon fiber has very high stiffness, okay, and their price can be even 20 to 500 times higher. Okay, high strength carbon fibers reach stress levels up to 7 gigapascal. Depending on the raw material and the manufacturing process, the stiffness can vary from 200 to 1000 gigapascals. So you see, steel has elastic modulus of how much? 210 gigapascal. So your carbon fiber can exceed much higher than steel. So you see how much like even a thin fiber can lead to such a high sort of thickness. And it can reach even very high strength up to 7 gigapascals. Now, carbon nanotubes also belong to the class of carbon fiber materials. They feature cylindrical atomic structures, the modulus and strength of. So now we are now in the recent years we have also developed fibers which in the nano, even in the nano, in form of nanotubes. Okay, so they are called carbon nanotubes. Okay, so you might have heard like CNTs, right? So these are very thin, 1 nanometer diameter structures. They are almost defect free, and they can even offer very high elastic modulus, such as about 1500 gigapascal, and even a strength can reach to 200, which is like incredible. Like we are now in the era of like 3 gigapascal or 7 gigapascal, but now these kind of structures they just offer like huge leap. So you can get about 200 gigapascal of strength, which is enormous. But obviously they cost like huge, like they are quite expensive, and therefore it's quite limited to in the current industrial use, right? So this is one example of this is a table that I was talking about. If you see again here, your carbon, so this is high modulus carbon. So if you see the strength is about 2.4, this high strength carbon is about 3.5. Okay. Whereas your E glass is about 2 gigapascal. Depending upon different sort of glass that we use. So these are the different things. So, but one thing to notice here is if you look at the failure strain. So these are the strength. Strength is, let's say if you have this load displacement curve, okay, this is the stiffness. The slope is the stiffness. So if this is your load, this is your displacement. This is your sort of slope will give you the stiffness. But let's say at which amount of displacement or strains it will fail. Okay, this is the load. So strength will give you the load at which it will fail. The tensile strength, that means the stress level at which it will fail, whereas the strains will give you will be driven by the displacement, right? So at what strain will your sample fail? That is again a parameter, right, to judge how much your structure has deformed before it fails. That's the whole idea. This one says how much the structure has taken the load before it fails. So if you look at the strains, you see that cellulose, although it has very low elastic modulus 80 and tensile strength is also reasonably all right, but if you look at the strains, it can really undergo very high strains, about 3%. So that is even higher than your e-glass and all the other things. So you see that the amount of strains, some of them can even go. Okay, so again, as I said, that it depends on the uh, sort of the applications what we are looking for, whether you want a structure to take more load or take more deformations, and whether you need something which is thermally expansive or conductive and things like that. So there are a lot of options available, and based on that you can make your own material, right? Own composite. Okay, I think this is something we already discussed in a while, but just to say that these kind of elastic modelers are very, I think, so I'll just skip it because this is something very similar to the graph that I showed earlier. Now, before going a little bit more further, now the question that is often raised is why these structures are so thin, why these fibers are so thin, right? So typically, if you see, as I said, that these fiber diameters can be 100 micrometer to 150 micrometer, right? Now the reason why these structures often are very thin is like, naturally, if you say that why not increase the diameter, probably if you increase the diameter, your bending stiffness also increases. So probably it should offer more strength against, or more stiffness against flexure or some other sort of, even for tensile strength, right? Now, the reason why the problem is something called size effect. We call it size effect. That means if you increase the diameter of the fiber, your ultimate strength, if you see in this figure, it basically falls down. And this is something has been has been observed long back. The reason is that goes to the concepts of fracture mechanics, where you can say that because of the size effect, that as you increase the size, although your material is same, your number of flaws also increases, number of imperfection also increases, and as a result, your fracture, the probability that it will fracture and the loads it will fracture it much lower. As a result, your tensile strength, it not drastically but linearly sort of reduces. And that's the same concept we offer. Let's say if you do a lab test for a small structure, if you want to scale up to a real structure, there is always this problem of size effect. That means it's not going to replicate exactly the same, because there in with fracture, when you're considering fracture, your number of imperfection also increases and all these sort of things, right? But obviously we cannot go really really small, but there's a limit to how small we can go, because the more smaller we want to go, the more complex the manufacturing conditions become and the cost increases. Now again, if you see, so therefore we have to be somewhere in the optimal, where we choose this should be some sort of a fiber diameter that is optimal for our case. Now if you choose, now again the question is, if you look at the length, how much length we should use. Okay, that is again a question. So how much diameter we should use comes from the last slide. How much length we should use comes from this slide. And if you see, if you increase the length, your strength also increases, but in more of non-linear fashion. So therefore, if you have a chopped fiber and if you have a continuous fiber, so chopped fiber will offer much lower strength, whereas your longer fiber will offer more increased strength or higher strength. The reason is also because there's something called the end effects. That means near the ends, where your structure is having subjected to some boundary condition or loads. So what happens is your stress become highly non-uniform here, and this is where the stress concentration increases. As a result, the failure increases drastically here. And for longer fiber, you have a substantial amount of region or substantial length where your sigma or your stresses, internal stresses, they are uniform in nature, so they don't really cause any failure. What in a case of small fiber is, if you see, there's not much of a uniform place left over, because it's just the edges, and it just falls down again towards the edges, right? Now, again, what is the strength obtained with long, like different sort of fibers, right? So now these fiber orientation. Naturally, if your fiber is oriented in the loading direction, it will offer the maximum strength, a maximum strength like tensile strength. If you pull it, okay. So naturally, if your fibers are parallel to the loading direction, it will have the maximum strength. But if it's in the orthogonal direction, it will offer something like. So the graph looks in this way, and this is something, I guess, quite intuitive as well. Okay, so this was more or less about the fiber part. Now looking a little bit towards matrix. Now matrix is the binding, as I said, is the binding agent on which the fibers are embedded or in which fibers are mixed, right? Now, your matrix material, although they don't offer any particular stiffness or strength, they are equally important because they are the one which binds. This is the one which transfers the load. Okay. So as a result, so these are very important in the composites, and therefore we have to choose them also wisely based on our applications. So now there are different kinds of matrix used. One of them are, the most common is the polymer based matrix, but we have also seen metal based matrix, ceramic based matrix, or even carbon and graphite based matrix. So carbon is something that can be used both as fibers but also in a matrix form, obviously in a different form, but then in a different in both configurations we can use. Now, in the polymeric matrix is further divided into thermoplast and thermoset. So, as you all know, that thermosets, they don't soften upon heating, and the thermoplastic can be reshaped, right? And then you have this metal matrix, which are aluminum, copper, titanium. Ceramics are something like carbon, calcium carbide. All these sort of ceramic materials can also be used. So, this is more or less the classification. So here are a few of the examples of thermoplastic polymers. And I think a lot of you who are working in the material science might know these sort of polymers, which offer very high toughness, high volume, and they are relatively low processing cost. They can work up to the range of 225. Now, in many of these thermoplastics, you don't need any curing for polymerization to occur, or very low temperature curing is enough. So this is one advantage in many cases where you don't have a let's say facility of a autoclave or a oven. So in that case, in many of these, thermoplastic can still be used directly without curing. So you don't need it to heat it, right? Okay, I think this. So next is your thermoset. Now the thermoset are something like polyesters, epoxy, polyamides. These are the main categories of these thermoset sort of matrix. And normally all of them have different properties, as I said. But like if you want to go for higher temperature, one might use this polyamide, or else I think this epoxy is quite often used, or polyesters are quite often used, right? And they can, but the epoxy, I mean, you need to cure it to a high temperature. Okay, so that means if you have using epoxy, you have to put it in a, you have to apply both pressure, you have, and as well as temperature, and therefore it has to undergo a certain curing cycle. Okay, that means you have to put in a certain pressure for some time and temperature for some time, then leave it like for some time. So there is a proper curing cycle, and at the end, you can sort of get the polymerized version when it gains the strength, right? And you have to heat it about 180 degrees. So you need to have these facilities in order to use these epoxies. So polymer matrix cannot be used near or above the glass transition. Every polymer has this sort of glass transition temperature, and you cannot use it. I think in one of the lectures we was about these kind of things, right? A few sort of different distinguishing parameters between the two. I'll just sort of leave it because I think they are something you can always look into it later as well. So I think the main idea is that thermoplastics are, they soften and they so can be reused again and again. So it's kind of recyclable. On the other hand, they don't, thermosets, they cannot be used like that. And another important part is this short curing cycle and this long curing cycle. Now, apart from this polymer-based matrix, we have also got metal-based matrix. Now, they are aluminum, titanium, copper, and different sort of things. Now, naturally, they are more heavier, right? And they are subjected to interface degradation. What do I mean by interface degradation is that means, let's say you have got some fibers, and then it is basically there is an interface between the metal matrix as well as the fibers. So that undergoes a lot of degradation, and if this bonding doesn't happen properly, it leads to sort of failure and also corrosion and all these sort of things. Okay, so one attractive feature of metal matrix is the higher temperature use. The aluminum metal matrix composite can be used in the temperature range of 300 degrees, whereas the titanium matrix can be used above 800. So these sort of have some applications in where you really need this high temperature requirements. Similarly, for ceramic matrix can be used, as you know, for even higher temperature, right? So their application also goes to around 2000 degrees centigrades. Now they have high elastic modulus, they have low density. On the other hand, the main disadvantage is they are very brittle in nature. Okay, and they are susceptible to flow. So it should be noted that the composite with carbon fibers, as I was saying, carbon can be used both as fibers as well as matrix. So it's called carbon-carbon composite. Now, in many of the space application, you might find its use. Carbon-carbon composites have been seen as a leading edge of the at the leading edge of the space shuttle, where the high temperature resistance is required. So the carbon composites can raise up to about up to 300. So I think even more. Yeah. So I think there are some ceramics which can even go more than about 2000 centigrades, and therefore they can be actively used in different applications. So these are some of the properties. And if you remember, the elastic modulus of carbon fiber was how much? Was about 200 gigapascal, right? Whereas if you see the matrix, if you look at the thermosets, it has just got 3 gigapascal, or thermoplastics. So it's quite low. So the polymer based matrix, you can clearly see that your stiffness is offered only by the fiber and not much by the matrix, right? You clearly see how much low is it. But on the other hand, if you see the percentage failure strain of these, some of these polymers, they are huge. That means your polymer can really undergo large strains. That means it can really deform to a great extent, right? So in that helps a lot in different sort of applications where you really need these large deformations. On the other hand, naturally, metallic matrices, they have large elastic moduluses, whereas ceramic has even higher elastic modulus, right? So if you need something that you need this sort of higher elastic modulus, so you would probably go with this kind of structure as well. And even they have relatively high also tensile strength. So as I said, this are now coming to these composites. That means the now we are talking about in the more macro level, where we already have the fibers, we already have the matrix. So this is ply or lamina. That means one layer. Okay. Now you are stacking different layers together like this. So one of them is 0 degree, one is theta, any angle as you like, depending upon what you want to get at the end. So you can stack different unidirectional or oven kind of fibers that we already showed you, right? Now, how does the effective property of this whole structure it varies? That is something very important. So naturally it varies. It depends on the how the fibers you're using, okay, how the matrix you're using, and then above all, it also depends on what the orientation, how you are orienting these fibers, which direction these fibers are oriented. What are the thickness of each layer? What is the thickness of each layer? Okay, can you hear me? Okay, I think so. Okay, so it's running, right? Okay. Okay, so what are the thickness of each sort of, and then what is the stacking sequence? How is the stacking? So let's say it also depends what is the first layer, what is the second layer, what is the third layer. If you use the same number of laminas or plies, but let's say first you use 0, 90, 90, but in the next you use 90, 0, 90, that will also change the properties. So the stacking sequence, the sequence in which you are stacking, it also matters. Okay. So just there is another type of actively used composites. They are called sandwich structures. Now these sandwich structures are something which consist of different composites on the end, but in the middle it has a thing called core. Now core is something that adds the bending stiffness. So as you increase the thickness, you will get higher bending stiffness. Right? So this particular thing increases the bending stiffness. Now, if you just sort of look into the whole picture, now you can clearly see that your factors in which the composite depends on the properties of the materials, the length of the fibers, the orientation, cross section, and so forth and so on. So these are few of the things. So I'll just quickly go through a little bit towards different manufacturing process. I hope you have got the idea of what are these composites, and you see that you can arrange in different stacking sequence. So if you just have 0 and 90, it is called cross ply laminate. Okay, something like 0. If you just have 0 and 90 angles, so this is called cross ply. Okay, this is called cross ply laminate. So this is something normally used in many of these applications. So what we'll do is we'll just quickly go through the manufacturing process and how these laminates are manufactured. Okay, so normally what you can see is you have this sort of different fibers and the matrix, right? As I said that there are fibers and matrix. Now these filaments are called individual fibers. So the fibers, they look something like that. So this is example of a glass fiber. It's just the fiber, it's not a composite. So you can just find these fibers available from the market, where these are filaments, the individual fibers. Okay, but when you have a bundle, it's called roving, and then this thick a big bundle that consists of many different rovings or many different fibers together. That's called tow. And then there's this something called fabric that I already showed you, that they're woven upon each other and they look like a fabric, right? Now we will discuss what are the different components that are required for the manufacturing. Okay, so this is something called a pre-preg. Now pre-pregs are nothing but they are available sort of, it is available material where it already have the fiber and already have the matrix together. Okay, so one thing what you can do is buy the fiber separately and buy the matrix separately and make the composite, which is this. So this is the carbon fiber, and you can buy a, let's say, epoxy or any sort of polymer which is in the liquid form, and then you can mix it and make the composite out of it. But another way, a more efficient way to do it is you can buy directly the pre-preg. Now pre-preg is something that consists of the fiber and the matrix already embedded. Okay, so what you have to do is, if it's a normally if it's a thermoset polymer, you have to put it in the, as I said, you have to put it in the oven, because thermoset polymers, they require polymerization or curing, right? So you need to put it in the oven and subject it to certain temperatures and pressure. Okay, as a result it will cure and you will get that particular product. On the other hand, if you go by the thermoplastics or some other which doesn't require any curing, you can directly use this sort of prepregs. Okay, uh, so so there are different sort of paths, we will discuss one by one. Let's say one of the manufacturing process, or the most basic manufacturing process, is called hand layup. Okay, that is something one can very easily do it in lab. Is like, what you do is, this is an example of hand layup. So let's say you first make a mold. So what is the shape? So if I, let's say, want to make a particular shape of a composite like this, okay, I will make a mold in this fashion. So once I made the mold, then I will put the fibers first on the top of it, on the mold. So let's say if this is your mold, I see the black part is something, uh, you put a paper or a coating on the mold so that it doesn't stick, and then you put the fibers. You see that these dry fibers are put on the top. Once you put the dry fibers, you put the your polymer or your resin. Okay, resin is nothing but the polymer. You apply the polymer, and then using a roller like this, particular roller like this, what you can do is you can press it by your hand uniformly, and then so that all the air bubbles comes out and you have a more uniform surface. and then you put a sort of tacky tape around this whole structure, and then you leave it for a while. So this will lead to something called hand layup. Now naturally this will only work, so this process works if you don't have to cure it. Okay, so these are polymers, let's say, which don't require any curing or very low temperature. In room temperature some polymers can cure, then you can use this sort of method. But if you're using something like a thermoset, where you need to epoxy, where you need to go very high temperature, then you can put this setup inside a same setup. What you can do is put it inside a oven, and then you can cure it. That is also possible. So naturally your mold should be something that is able to resist very high temperature. Okay, that is also something which is possible. But naturally, because everything is done manually, there can be a bit of poor quality of the material, and if you don't consolidate or put enough pressure, it can lead to some sort of a non-uniformity. Now, in order to mitigate this sort of non-uniformity, another way of doing it is using vacuum. So you use the same kind of thing, but now you use, let's say, a vacuum bag and some more sort of plastic material, so that what you do is you use the same sort of hand layer, but now you put a vacuum instead. Now, what this vacuum will do is that it will create a vacuum, and excess whatever is the, so it will make a uniform surface. Whatever you are doing with your hand in the consolidating process, now what you can do is just do it with a vacuum, so it will be much more uniform. And whatever is the excess resin or excess whatever you have added, if it's too much, it will be flown outside. Then you can do something called press molding. So this is compressive press molding. That means you have your mold or your sample, and then you put some pressure and temperature on the top. So these are particularly this kind of press molding is more useful if you need to apply this polymer, if a polymer requires temperature as well as uh, temperature, or it needs something like a pressure. Okay, so we will see this video. So you see that this is the sample, and now what we do is we put it inside. You can use a mold or anything as well, and then it's compressed. Okay, so these are these prepregs. This is a roving. Inside the roving, there are different prepregs, and you cut it in a certain shape. So you get this particular prepreg, and then what you do is you make the different stacking sequence. So whatever how many layers you want to put, 0, 90, 45, whatever you put, you make cut it into a desired shape, whatever you want, and then put it inside this compression mold. Okay, you have this compression mold, and you put some compression force for a particular pressure as well as temperature. Both you can apply, you can control the temperature, and you can also change the pressure, and as a result your polymerization will occur, and you will get the desired shape. You will get a desired property or desired shape of a composite. After cooling down, the cure part is got. So the only advantage here is like it has got the limited size, because your compression press molding is a limited machine. You cannot have very large structure out of it, because you need very big compression mold structures. So another method is called resin infusion. It's a bit different from vacuum that we already discussed. Vacuum induced layup. This is called some, here also we use vacuum, but it is called vacuum assisted resin injection. Okay, so it's a bit different than what we did earlier. That time what we did, we have created the vacuum to make it a uniform surface. In this case, we create a vacuum so that your resin flows automatically, because once it's created a vacuum, okay, all the air has been taken out, so there is a sort of pressure difference which creates, as a result your resin flows from outside to inside that lamina, okay, or particular. And here you can use really complex shapes, and your void will be very low, because you're creating a vacuum and allowing the resin to move inside. Okay. We'll see a quick video again. This is called liquid resin infusion. Okay, so this is a technology being used, if you see, for a large sort of wind turbine blade. So wind turbines blade, if you have seen, they are huge structures. They are very slender, and they are made. Most of the wind turbines are made in with glass fiber composites. Okay, so this is how it is normally made. So first, what you have done is you have made a mold like this, and then you have put this different pre-pregs, or first you can put your fibers and resin, both you can do, but this is a pre-preg. That means it consists of both the fibers as well as the matrix, and you put it in a desired shape like that. Now you cut all the edges, you put a ply, okay, so that you separate these whole things with the resin. Now you put a setup like that, okay, you seal it. Now why this is very important, because you need to create vacuum throughout the whole structure, and if you don't seal it properly, so your vacuum will not be created. And now you connect it to a sort of vacuum pump, and you see there are different inlets connected here, which goes inside this sort of mold. Okay, you put a vacuum bag. Vacuum bag is something which helps you to create the vacuum, like you find it in a vacuum cleaner. Okay, this sort of material, and then you connect it with the chamber where the resin is stored. Okay. So once you're ready, you allow your resin to flow inside. Once all the, like, you've created the vacuum. Once you've created the vacuum inside the whole structure, your
Excuse
resin will.
me, sir.
Yes, yeah.
Sir, are you showing the things? We are not getting anything here.
Oh, really? Oh,
Yes,
okay. You should have told me earlier.
I didn't understand, sir, initially.
Okay. Anyways, I will. Oh, I thought you are just seeing the films.
Up to this, it is okay. After that, we are not getting.
Okay. I guess the problem is something here. So, just a second. I think maybe that particular screen was not shared, or just let me know if you are able to see or not. Okay.
Up to this, it is okay, sir. After that, we didn't get.
This one you saw?
Yes,
Okay.
we got it.
Okay. Just a
But the
second.
explanation part, we didn't get. The next portion.
Oh, I think it just started. Yeah. Just a second. I will. What I'll do is share the other screen. So can you see now?
No, sir, there is no, your screen is not being shared.
Okay.
It's visible now, sir.
Okay. Yeah, because I think I had two screens, and one of them was probably there. That's the reason. Just a second. I think I have to open it again. So just let me know if you can see this video now. or it's just still?
Yes, sir, we can see.
You can see the video, right?
No, video is not working, sir. Is it the video?
Yeah. What you
Yes, yes,
see?
yes. It is working, working, working.
Okay, it is working. Okay, I'll just simply show it again. So see, this is the video of a wind turbine blade, like manufacturing of a wind turbine blade, and they are using this sort of technology that I said is called VARTM, so vacuum assistant resin transfer technology, right? So what we are trying to do is we make this mold, we use this pre-plies, which consists of this fiber and the matrix, and then you have these different layers, and then you're connecting it to a vacuum system. So once you're doing it a vacuum system, the resin will flow inside, and that's what is happening. I'll just so you see all these systems have been connected. So all these channels are implemented inside, and sorry. So you see that once we allow the vacuum, this resin starts to flow like this. So it will flow all throughout this particular mold that we have created for the rotor blade, and so you're kind of filling the whole channel and the whole mold using with the resin. So now you see how the resins are uniformly getting filled. So if you don't do it, what will happen is there is a chance that there are air voids, and these air voids will create defects in the structure and lead to lower strength. To avoid that, that's why we use the sort of vacuum assisted technology, right? So that's quite a popular method to use or make this kind of structure, especially for larger structure. This sort of helps. Okay. So once it all your rotor blades are covered, then what happens is like you start show you close it, right? And now you heat it, you mold it. This mold is under a heater, and you heat this whole mold. You stop the connection, you stop the flow, and then you heat the whole sort of mold until it polymerizes. Okay. Now, once it's already cured, you cut, you do demolding. The demolding means removing the mold. Okay. And let's say you apply if it needs, because these rotor blades have got some stiffeners inside. So you apply this sort of stiffeners. And then at the end, you put another rotor blade on the top like this. So you do the same process again with the upper blade, and you connect it. So at the end, you get this sort of nicely looking rotor blade, which is often that you have seen, right? So this is an example of how such kind of things are created. Now, there's another method normally used for chopped fibers. So when you're using chopped fiber, as I already discussed, these chopped fibers are having lower strength, but they are also more extensively used in several applications. And for this, we use something called a spray layer, where you have got a spray gun, where you have the resin, we have got the fibers, and you spray it all over. So as a result, you will have a uniform distribution of fibers and matrix throughout the whole mold if it requires, right? And then this is something which we use very often, and this is called the pre-preg. So you just use a pre-preg, like I showed earlier. You use the mold, you put the pre-preg, and then you simply put it in your oven or your autoclave. Now, autoclave is a bit different from the oven, because the oven just allows you to control the temperature, whereas autoclave, it has both pressure as well as temperature. That means you can control. So this is a typical example of a curing cycle. That means how you're curing, how your process temperature and pressure are going to be changed or needs to be changed in this particular autoclave, so that you get a perfect polymerization, or you get the maximum strength of the polymer, right? And this is an example. Let's say for certain time you have to increase the temperature for this much amount, and like this you have to go on. Okay, so this is again, okay, what I'll do is also run a small video here. This is an autoclave molding of prepreg. Okay, I think this is quite. So this is how autoclave sort of looks like. So you have got a plate that consists of the mold. So you prepare this mold. We have to prepare this mold earlier, let's say made of stainless steel or which can take this high temperature. And these are the prepregs. You cut it, and this is a cutting table. Normally we using this cutting table, we cut it and then accordingly put it over a particular mold like this. And then you put the stacking sequence again, depending upon what are your applications. You put the stacking sequence and everything, and then you put it inside the oven. Sorry. So once you put inside the oven, you heat the oven, and so what you can see is that, I think something wrong with the video. So you can see that there is some sort of the oven. Basically you have to then cool it down, okay, and then do the demolding process. You take it out, so you have to control the temperature and pressure, and then you make this whole lamina. Okay, I hope this is clear. Something is wrong. I think it's trying to save. Okay, so moving forward, I think there is a couple of more techniques we'll just briefly discuss. So one of them is this called automated. So pultrusion. Pultrusion is something we'll just quickly discuss. So if you need to make a beam or a I section beam, let's say, okay, or a different section that consists of let's say circular cross section or I section beam, what you will do is there is a process called pultrusion. As the name suggests, it's pull plus extrusion. That means you pull the fibers through this preheater, so it's already getting heated. You apply the resin here. Okay, that means your fibers soak the resin, and then you put it in a heater. So you allow it to cool, and as a result, what happens is using some pulling technique, there are some sort of a dies here. What this dies does is it will create a certain shapes. If you want to make a I section, it will have a die of I section, and all your fibers will be getting through that I section, right? And then you make that particular sort of shape. So I think just quickly show you. This is how a pultrusion system works. So as you see that there is a sort of fibers. The fibers are coming from this roving, and it is dipped inside a resin bath. Okay, so you see that it goes, the fibers get wetted, and then there is a particular shape what you want. In this case, it's a circular shape. So you will make a die of circular shapes where the fibers are going like that. So if you want to make a I section shape, you can also make a I section shape, or any L section shape, you can make a L section, depending upon the shape that you require. And then you just finally heat it to a particular temperature, right? And at the end you get the sort of product like that, you see. So it is basically heated to cure the resin matrix like the polymer. And then finally you go here, and there is a saw line which cuts the particular shape, and you will get a tube structure, for instance, a carbon fiber or a fiber reinforced tube structure, right? So this is already discussed. So I have a couple of more slides, and then we'll finish. So now moving a little bit forward. Now, what in the recent times, what you have seen is we have been using, manufacturability have been expanded immensely, and we are getting into more sorts of. You might have seen robots working for manufacturing purposes, and this is one example how this something called automated tape layup. That means you're laying up the tapes. A tape is something which consists of many fibers. So you're laying up the tape with a robot arm. Now, what the advantage of this is, like, if you want to make in a more curvilinear fashion, if you want to make a fiber orientation in a curved way, what you can do is you can allow your robot to move you define a certain trajectory, and it will go in a certain sort of direction. And they have got heater as well in the head of the robot arm, which kinds of heat it. So it can control, you can heat the fibers and the matrix or the tapes, and then at the same time you can lay it up. So it heats it up, it cures it, and then it goes. Okay, that is obviously it's more expensive, but I think the new Airbus aircraft, the fuselage of the aircraft was made using this technology, and it's something like this. I think this is a better picture. So a 350 aircraft, the upper fuselage was made using, and you can clearly see how much ease it is. So making this in other ways, it's very difficult because you need to have a very big mold, you need to have a very big heater. It's common, like you saw in the rotor blade example, right? You need to have really big heater that would heat inside. So now in this case, you don't need any of this. You just need a robot, and that can really go from one direction to another. So this is a technology that has been recently explored. I think in India we have in NAL, National Aeronautic Laboratory, and we have one of these. But I think I'm sure in the coming time a lot of things will be explored in that sense, right? So I'll just quickly show. So this is a video of German Aerospace Center. So I was lucky to work there for a while, and you see that this is how these robot arms work. Okay, so you see that basically it's laying up in a particular fashion, and it goes from one direction to another, and it's heating at the same time. And you can get a particular plate, and you can do any sort of. So this is angle. You are putting it in an angle now. Okay, so as I was saying, so that is the whole idea. So you can get a plate of different kind of things. Again, these are a few more examples. So again, just at the end, I'd like to say that these thing depends a lot how are you cannot really make a big circle because your fibers will start breaking. So there's a limit to the steering radius. Okay, depends obviously on the fiber and the resin. So one last thing. So this is again collaboratively you can work different robots. But one last thing we want to show is something called the 3D printing, and this is a machine we also have it in IIT BHU where we are working on it. So this is a printer, 3D printer that where you can make composites. So there are two sort of nozzles. One you have the polymer going inside, and the other there is a this fibers going inside. So once it goes inside, there is a heater, and from this heater it sort of extrudes the resulting material that consists of both fiber and the matrix, and you can really make into different shapes and work in different sorts of angles and do different shapes, right? So this is, for instance, I mean, this is something example of a sort of fiber, how it looks like, fiber composite, which consists of carbon fibers and epoxy matrix. So just for example, I guess, yeah, more or less, these are some of the things. So you normally have to use these things, and that's it. Yeah, I mean, that's how I conclude. Thank you very much for your patiently listening. I hope if you have any questions, feel free to ask. Yeah, I mean, I have covered few of the important things, but if you have or any other questions, feel free to ask. You can email me if you have some doubts as well, or if you want to know more about this subject, I'm happy to help. Okay. Okay, thank you very much.
Thank you so much, sir, for such an enlightening session. Uh, so you'll be taking questions, right?
Yeah,
So all
sure.
the
I'm happy
participants
to
are,
take any
yeah,
questions.
yeah. So all the participants are requested to uh, ask questions if you have any. So does anyone have any questions right now? Okay, I don't think there is a question.
Okay, no
So
worries. If you have anything, you can ask them to later reach me as well. That's not a problem. Okay.
yes, sir. So, sir, thank you for being here with us. Thank you for sharing your knowledge with us. So now I request our sir to share the digital memento. Hello, Anuprata sir.
Madam.
Yes, yes.
Madam, just 1 minute. I will share it. Just 1 minute, ma'am.
Yes, yes. So please wait because there is a digital memento prepared for you.
Okay, okay. Okay, no problem. Yeah. I'll be waiting. It's fine.
In the meantime, all the participants are requested to fill the feedback form that is already shared in the chat box. Shourav Chatterjee says, "Nice session, sir. Thank you." I think sir will read
Thank
it.
you. Thank you.
Please fill up the feedback form in the meantime. Anubrata sir, are you here?
Shubhanurekha madam, just wait. Actually, there is a network issues. Just wait.
Yes, yes, yes. I understood. Oyan sir, please wait. We are very sorry for the inconvenience, but there is a network issue right now going on.
Okay, no problem. I'm
Yes,
just here.
yes,
Yes,
madam. Shubhanurekha, madam.
yes.
Now,
Yes.
now I will share it.
Yes, Anuprata sir will, Dr. Anuprata Mondal will share the digital memento prepared for the speaker.
Shubhanurekha, madam, kindly co-host me. Actually, I'm not
Okay, I'm
co-host.
trying, I'm
That's why
trying, I'm
I
trying.
can't share. Tanmay sir, are you present, sir?
I think
Kindly
I cannot make
make
you
me co-host.
co-host because I'm not the host.
Tanmay sir, Tanmay sir, please make me co-host.
Sir, let me share the digital memento, please, because if I can do that, I'm doing it.
Yes.
Because I cannot make you a co-host.
Shubhanurekha,
I'm sharing the.
Shubhanurekha, please
Yes,
share
yes, yes.
the digital
Yes,
memento.
I will, definitely. Is it visible?
Yes, yeah. It's visible.
Yeah, sir, please accept it from our end. Thank you for
Thank
being
you
here
very
with
much.
us. Thank you for sharing your enlightening knowledge. So,
Thank you. Thanks a lot for the invitation. Yeah, I hope you enjoyed, everybody, and thanks again for the memento. Yeah, it's a pleasure.
okay, sir. Okay, thank you, sir. Thank you so much, sir. If
Okay.
you, yeah, all the participants are requested again to fill the feedback form that is given in the chat box and will be shared in the WhatsApp group, I guess.
Participants are also requested to please fill up the assignment. That is, it will be shortly shared to you in the chat boxes. Please.
Yes. And our second session will begin at 2:30 p.m. Please join on time. It will begin from 2:30 p.m.
Thank you. Okay, thank you.
Okay.
Alex,
All the participants are requested to fill up the feedback and also the assignment that has been given to you in the chat box. Please fill it up from your end. So once again, thank you to all of you. We'll meet at 2:30 p.m. for the valedictory sessions. Okay, so thank you all.